last time I explained Huffman codes. And Huffman code uses variable length codes. So we can reduce the total number of bits to express, to represent the string. And to create the Huffman code, we used this algorithm. First, we enumerate all characters, and then we select two least frequent characters, and then merge them. And we add these two frequencies and make this. And then we repeatedly apply this until we create a single tree. Then we assign code words to characters in this way. A is 0, and B is assigned to this code, 1, 0, 1. And for C, we assign 1, 0, 0. And D is 1, 1, 1. E and F are 1, 1, 0, and 1 and 0 respectively. So first, we create a tree like this, and then find code words. Okay, then I will explain the running time of this algorithm. Its running time is n log n. So try to understand the running time. Let's think about the naive algorithm first. First, we have to find the smallest number in this array. So what is the running time to find the smallest number in this array? 박종훈, what's that? Constant time. Assume that in this case they are sorted, but we don't we don't sort them. N, yes. Big O of n time to find the smallest one. And then we have to find the second smallest one. It also takes big O of n time. So we do this repeatedly. How many times do we have to do this? 박근배. Yes. So there are n-1 iterations. So the total running time is big O of n squared if we use a straightforward approach. But if we use a heap, we can do it better. Okay. How can we improve this? I mean, how many times do we have to run the extract max in an iteration? One extract max for an iteration? Kim Jong-bin. Twice. Yes, we have to select the smallest and the second smallest. So we run 2 extract mean operations. Okay? Extract mean twice. And we need one more. What is it? So after 2 extract mean operations, these 2 elements are removed from the heap. And then we have to add this into a heap. So we need a heap insert operation. And what's the running time? It's also, insert. Heap insert. And what's the running time of this? It's also big O of log n. So all these operations are performed in big O of log n time. And we have n-1 iterations. So the total running time is big O of n log n. And let's talk about the correctness of this code. So before I explain this, I will clarify this notation. I will explain the cost of a tree. The cost of tree T is the product of the sum of product of this f of c times d of c sub t. F of c is the frequency of a character c, and d of c is the length of code word for c. So it is I'll give you an example using the tree T. Assume that f of x is, and the frequency of x is this, and f of y is this, f of a is this, and f of b is this. Okay? 30%, 20%, 10%, and 40%. Then the cost of 3t is the frequency of x times the depth of this node, which is 2. And then the frequency of y times 1, and the frequency of a times 3, and frequency of b times 3. Yes, this is the cost of the tree. Okay, keep this in mind, and let me explain the correctness of the Huffman code algorithm. I'll explain 2 lemmas, and they are quite long and not easy to understand. So this is the first lemma. And for a couple of minutes, try to understand this lemma, what it claims. So first, we find 2 least frequent characters and then merge them such that they are siblings. Okay? So the lemma justifies this. We can do this. Okay? Why? The proof is given here. Okay, read this proof. Okay, can you prove that? Can you prove that? So, sometimes you can understand that something is correct, but it is sometimes very hard to explain or to prove. Then you have to try proof by contradiction. Okay? Assume that there is an optimal tree where x and y are not siblings. Okay? Then let's see this. First, exchange x with a. Then how about the cost of t prime? So because the frequency of x is smaller than the frequency of a, the cost of t prime is smaller than or equal to that of t. Okay? And moreover, we know that the frequency of y is smaller than or equal to that of b. Exchanging y and b decreases, or at least the same as the cost of t prime. So this is also an optimal prefix tree. So there exists an optimal prefix tree where the two least frequent characters are siblings. Okay? Okay. So until now, I justified the first step of the Huffman code algorithm. We can merge two least frequent characters and then try the next iteration. But next, I have to justify that after the n-1 iterations of the same step, we can get the optimal Huffman tree. And this lemma explains it. Okay. Try to read this. We need one more lemma. That's by exchanging z, by exchanging z by the subtree. Yes, that is this. Okay. So let me explain using an example. So we are going to find an optimal prefix code and prefix tree t with 4 characters. And then we know that x and y are siblings. So we merge x and y and create a subtree like this and replace it with by z. Then we apply the same algorithm recursively with only these 3 leaves. And then in some way, we can create an optimal prefix tree t prime for these 3 characters. Finally, we replace z by this subtree. It is this. Then we can achieve t what we wanted. So if we prove this claim, then the correctness of the Huffman code algorithm is proved. Okay? Not yet. Let's go back to the algorithm. So in the first iteration, we have 6 characters. In the second iteration, we have only 5 characters. And we don't touch into this subtree. So that is, we consider a different problem, not so much different, a similar problem with 5 character input. Okay? So, and then after solving this problem, we replace this leaf by this subtree. That's what we did. So if we prove this lemma, then the Huffman code algorithm is justified. Okay, and the proof is, the first part of proof is this. That is, the cost of t is the cost of t prime plus this part. Okay, try to understand this. Okay, look at this. These 2 characters are the same in their frequencies and depths. So, no changes. And then,
그리고 x와 y의 t에서의 뎁스는 그 t 프라임에서의 z의 뎁스 더하기 1이고요. 그래서 앞에 거에서 저 fx dx랑 fy dt를 더한 값은 그 fx와 fy 더한 거와 그 둘의 뎁스를 곱한 거랑 똑같은데.
Okay, I think you understand this. Okay. So in this case, fx times 3 and fy times 3. Okay? And in this case, you know that it is fx plus fy. So fx times 2 and fy times 2. So in this case, the sum of the cost of t is bigger than the cost of t prime by fx dog fy, fx plus fy. Okay? Yes? Okay. I will, after this recording, I will get back to Korean and you will understand easily. Okay? So it is this. So we get this. The cost of t is equal to the cost of t prime plus f of x plus f of y. And then this is the final part of this proof. Okay. The last page. Now, this lemma claims that if we create a optimal tree, optimal cost tree t prime using 3 leaves, then by removing z and attaching this subtree, we can get an optimal cost tree t with 4 leaves. So that's the claim. Then I will prove that it is true. So I'll prove this by contradiction. Assume that even though t prime is optimal for 3 leaves, but t is not optimal for 4 leaves. Okay? Then, because this is not an optimal tree, there is an optimal tree with 4 leaves. And by the previous lemma, there is such tree that x and y are siblings. And let T double prime denote it. So D double prime is an optimal tree with 4 leaves and x and y are siblings. Okay? Then let's do the same cut and paste technique. Let's remove this and replace it by z. Okay? Then the cost of T triple prime is, okay, let me write. The cost of T triple prime is the cost of T double prime minus f of x and f of y. And I also said B T prime is B of T minus f of x and f of y. Okay? And we assumed that the cost of T double prime is smaller than the cost of T. That was our assumption. This is optimal, and this is not optimal. So the cost of this is smaller than this. Okay? Then the cost of T triple prime is smaller than the cost of T prime. Because look at this part is the same, and this is smaller than this, so this is smaller than this. Then there is a contradiction, because this should be, and I said this is the optimal subtree with 3 leaves. So this is impossible. So by contradiction, our assumption that T is not an optimal tree is false. So this should be an optimal tree, optimal cost tree. Okay, let's wrap up this class now and see you on Friday.